Okay, welcome to lesson 7.2 on compound angle formulas. Um, so we're going to come up with some identities that are true for all values of the angles A and B. You can see them down here in the box. There's several angles. And compound angles just means that we're adding or subtracting two angles together. So we're going to be talking about what happens when I have an angle A plus an angle B. In order to come up with these formulas, like a lot of smart mathematicians a long time ago got together and they came up with the proof for why these things are always true. If you want to see a quick demonstration of the proof of a few of these, you can watch the video link in the lesson. I'll include it as well online on Google Classroom. And then he talks about how to come up with the formulas for tan, but it's just substitution and simplification. I'm sure you can find those videos on YouTube as well. But we're just going to go with these guys are true. So when I look at the two sine formulas, I notice that they're really similar. For sine of a plus b, there's a plus in between, and for sine of a minus b, there's a minus in between. Those are the only differences. For the sine of two angles, I take the sine of the first angle times cos of the second, and then cos of the first angle times sine of the second. For the cosine formula, it's a little bit different here. When I have an addition in the a plus b of the compound angle, then I'm going to see a subtraction in the expanded formula. And for a subtraction in the compound angle, I'll see an addition in the expanded formula. For cosine, I'm going to do cosine of the first angle times cosine of the second angle, and then subtract sine of the first angle times sine of the second angle, and that'll give me the cosine of the addition. For tan of the addition, again, looking for some similarities and differences between tan of a plus b and a minus b. For a plus b, I have an addition in the numerator and a subtraction in the denominator, and it's just the opposite in the subtraction formula. For tan of a plus b, I'm going to do tan of the first angle plus tan of the second angle, and then put that all over 1 minus tan of the first angle times tan of the second angle. All right, so why do we need these formulas? Like, what are we even going to use them to do? So we're going to use these formulas to help us simplify other expressions, to help us determine some exact values for angles that are related to different acute angles. So we've looked at pi by 3, pi by 4, and pi by 6, but what happens if I have a pi by 12, or an angle related to that, or a 5 pi by 12, or an angle related to that? So we're going to take a look at some of those examples. We can use this to prove identities. So other statements that are true for all values of theta. And then the last thing we can do is use them to solve trigonometric equations. We're going to look at some examples of all of these things. I'm going to save solving trigonometric equations for section 7.5 and 7.6, so we'll come back to that. Our first example, simplifying expressions. It says use the appropriate compound angle formula to create an equivalent expression for tan of x minus pi. So for this one here, I'm going to go back up and I'm going to be looking for tan, and I'm looking for a subtraction of two angles. So I'm going to use this formula right here, tan with a subtraction of two angles. And I'm just going to substitute into that formula. So I know that my formula is tan of a minus b is equal to tan of a minus tan of b all over 1 minus tan a times tan b. Now in our question, we've got an a that is an x and a b that is a pi. So I'm just going to fill that in. So every time I see a b, I'm putting in a pi, and every time I see an a, I'm putting in an x. And now we're going to try to simplify this. So now we do have a variable x, and we're going to have a variable x in our final answer most of the time if the question starts with an x. But what I want to do is try to simplify the tan of pi. I do know, and I might be thinking about the graph of tan of x, all those like squiggly lines and vertical asymptotes, or I might be thinking about rotating around the quadrants and landing on the pi and thinking about the fact that I know that tan of x is the y coordinate divided by the x coordinate. But either way, I know that tan of pi is equal to 0. So I'm going to substitute that in. Now on the bottom here, this kind of looks confusing, like what am I multiplying by 0? So I'm going to add a second set of brackets. I'm multiplying the whole tan of x times 0. And so when I simplify now, the numerator, it's just tan of x. And in the denominator, I have 1 minus 0, so I just have 1. And again, I can simplify that out to tan of x. So we made our first expression a little bit simpler. All right, taking a look at our second example, we're going to state exact values. So I want to determine the exact value for the trigonometric ratio sine of 11 pi by 12. Now 11 pi by 12 is not one of our special triangles, but it is telling me that I have to use exact values. So it's saying like eventually you're going to use special triangles or special angles. So what we want to do is take 11 pi by 12 and turn it into some special angles. And so what we do for this, I've got a lot of writing here for you to add to your note. I didn't want you to watch me write it all. What I'm going to do is take the given angle and I'm going to split it into an addition statement. So I've got 11 pi by 12. I'm going to split that into a pi by 12s plus b pi by 12s. And then I'm going to use numbers for a and b that will reduce to special angles. So for a denominator of 12, I can use the numerators 2, 3, 4, 6, 8, 9, or 10. They're all going to reduce to special angles when I put them over 12. Obviously, I can't use something like 5 pi by 12 because 5 pi by 12 won't reduce into a special angle, and I know I have to use those. So we actually have a couple of choices. Sorry. We actually have a couple of choices for this question. I'm going to rewrite sine of 11 pi by 12. So here in green is the work that I would actually write in this question. I'm going to rewrite 11 pi by 12 as some combination. So I'm going to pick two numbers that add up to 11, basically. So I could use 2 and 9, or I could use 8 and 3. I have a couple of choices. Either way, you're going to come up with the same answer as me. I'm going to use 2 and 9. So I see that 2 pi by 12s plus 9 pi by 12s, that's the same as what I started with. It's the same as 11 pi by 12. But now I can reduce each of those. So 2 pi by 12s, that's just the same as a pi by 6. And there's one of our special angles. And 9 pi by 12, that's just the same as 3 pi by 4, which is related to our special angle pi by 4. It's just in a different quadrant. So now I'm going to use my sum formula or my compound angle for sine with an addition. So I'm thinking about that sine of a plus b formula. So you might have that like up on your sheet beside you as you do this. We know that sine of a plus b is just sine of a cos b plus cos of a sine of b. So I'm going to use this idea, but here my a is pi by 6 and my b is 3 pi by 4. So sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. And now I can try to simplify this by filling in what I know. So for pi by 6, off in my rough work, but I'm going to show this. I'm still writing in green here to show that I am still going to show this. For pi by 6, I know that the opposite side is 1, the hypotenuse is 2, and the adjacent is root 3. And I'm going to use this triangle to help me figure out, well, what is sine of pi by 6 and what is cos of pi by 6. So I'm just putting all my answers in brackets so I don't forget to do some multiplication. So sine of pi by 6 is going to be the opposite over the hypotenuse, so 1/2. And cos of pi by 6 is the adjacent over the hypotenuse, so root 3 over 2. So there I've got my first two ratios filled in. Now I need to figure out, well, what is cos of 3 pi by 4 and sine of 3 pi by 4. So this is not an acute angle. So I'm going to draw my quadrants, and I know that 3 pi by 4 is over here in quadrant 2. My related acute angle is pi by 4. And so when I draw my triangle, I know that my opposite and my adjacent are both 1, and my hypotenuse is root 2, but I am in the S quadrant, so my sine ratio is going to be positive, but my cosine ratio is going to be negative. So I can come back over here, and I know that the cosine of 3 pi by 4 is the adjacent 1 over the hypotenuse root 2. But I can simplify that, so cosine of pi by 4 is 1 over root 2, but we know that you can write that as root 2 over 2 in simplest form. So root 2 over 2, but I'm in the S quadrant, so this is negative for my cosine. And then for the sine ratio, it's also 1 over root 2, but again, I can simplify that in simplest form. That's root 2 over 2. I'm in the S quadrant, so this one's actually positive. And so now I'm just doing some simplification with the math. I've got multiplication of two fractions, so multiplying the numerators and multiplying the denominators, and then again multiplying the numerators and multiplying the denominators. And then I can add these two things together. I'm also going to switch the order here, so I'm going to have root 6 minus root 2 instead of writing negative root 2 plus 6. It's just a little bit cleaner this way. And then that's over that common denominator 4. And there I am done. You could check your answer for this question by typing sine of 11 pi by 12 into your calculator, writing down the decimal in your margin, and then typing root 6 minus root 2 in brackets, and then all of that divided by 4, and you should get the same decimal. All right, the next one, we're going to prove identities. So an identity is true for all values of theta. When you're proving an identity, it's really important that you don't move back and forth across the equal sign. I can't add and subtract things back and forth or multiply, divide. To prove an identity, every time I'm seeing that word prove in my instruction, I have to separate the left side and the right side and work with them separately. So that's what I'm going to do first in my solution. The left side of the equal sign, so I'm splitting it down the middle of the equal sign. The left side is cos of pi by 2 plus theta, and then the right side is negative sine theta. And so what I want to do is manipulate these two expressions, or maybe just one of the two, until it looks like the other. A good rule of thumb when you're trying to prove an identity is start with the more complicated looking side. Not that that's always going to work, but it's typically you want to work with the more complicated and make it simpler. It's harder to take something simple and make it more complex. So I'm going to start over here with my cos, and I've got a compound angle. I've got an addition of two angles. So I'm thinking about my formula for the addition of two angles with cosine. It tells me to do cos of the first angle times cos of the second angle. And then if it's an addition in here, I'm going to subtract between these two parts. And now I'm going to do sine of the first angle times sine of the second angle. And again, I can simplify this. So because I've got pi by 2, I'm thinking about either on the rotation, I'm thinking about being at a rotation of pi by 2. And then I might be thinking about how sine of theta is related to the y, and cos of theta is related to the x of this point. And when I look at this point here, the point is 0 and 1. Or somebody else might be thinking, so somebody else's rough work is going to include a sketch of both curves. So they're going to do a sketch of the sine curve and a sketch of the cosine curve. And they're going to label what's happening at pi by 2 because this question involves a pi by 2. So they're going to be labeling that to come up with those two heights. And then, of course, they'd label that the red here is cos theta and the blue is sine theta. All right, so we've got our rough work. You're looking at one of these two diagrams. You wouldn't do both. And we can see here that cos theta, it's the x value, so it's 0. Or if you're looking at the curve, the height of the cos curve at pi by 2 is 0. So I know the cos of pi by 2 is 0, and I'm going to multiply that by cos theta. And then I need to figure out sine of pi by 2. So again, I can be looking at the terminal arm and I'm looking for the y value for sine is 1, or I might be looking at the sine curve and at pi by 2 there's a height of 1. Either way, the answer is 1. And now I can simplify this. 0 times cos theta, that's just 0, and I'm just left with negative sine theta. And what do you know? That's what we were looking for. So that is my right side, and therefore I can say that this statement is true. So cos of pi by 2 plus theta does in fact equal negative sine theta for all values of theta belonging to the set of real numbers. So this statement, this symbol here, it says for all. It's another math symbol for you. All right, good luck with your homework.